In continuing with the previous lecture on metal matrix composite manufactured through additive manufacturing, so we are now going to look into different types of matrix. How are these matrix formed using additive manufacturing? Matrix and composite formed using additive manufacturing. So, we have ferrous matrix, we have titanium matrix. So, when we talk about ferrous, people very commonly use 316, SS 316. If you talk about food processing, they talk about SS 316, they talk about bearing applications. Heavy industries, SS 316 is very commonly used. Now, using this SS 316 and reinforcing with TiC to form a metal matrix composite will be our discussion. 316L is a promising austenitic SS to manufacture component because of the ductile matrix property. If you have brittle matrix property, then adding this reinforcement is not going to take us anywhere. So, it is always a good idea to choose a matrix which has ductility. Overall, it is a good material for particle reinforcement. So, this ductile matrix is very good. So, that is why we always prefer, if you see Al, copper, then we used to do aluminum, then we used to do iron, all these fellows are having ductility inbuilt in their material. So, overall it is a good material for particle reinforcement. TiC is commonly used with ferrous alloys due to its high melting temperature. Ti6 has high melting temperature, then reduced density, superior corrosion resistance, increased hardness, thermodynamic properties and thermal stability. So, all these things are there. When TiC is added to ferrous alloys, it tries to have improve or increase the melting point, then reduce the density so that it can float or some application, then superior corrosion resistance because steel always has a problem of corrosion, increased hardness, then thermodynamic property while conducting and other things, and thermal stability. Metal matrix composite hardness and wear qualities depend on structural restriction like volume percentage and magnitude of filler material, dispersion of inserted elements and interfacial joining with the matrix and filler material. So, this all is going to be the advantage which metal matrix has. If there are no manufacturing fault, more strengthening component increase composites density, hardness and elastic modulus. So, this is also part of the metal matrix composite which is made through additive manufacturing. There is a big difference in the properties of additive manufacture because here it undergoes a quenching cycle, grain refinement. So, you will get a better property response compared to that. The solidification phase of 316 SSTiC composite, the reaction within Ti and C to form TiC is considered by the higher activation energy. First we are trying to mix Ti and C. So, that is because of the higher activation energy. This reaction takes place vigorously because of their exothermic nature. Ti and 6, because of their high activation energy, they try to mix and they form a TiC, and which is a stable phase. The possible reaction of Ti6 formation and the associated variations in the enthalpy and Gibbs free energy are thought to communicate with two temperature extent as illustrated below. So, Ti plus C gives you TiC, where T is lesser than 1939 Kelvin. So, delta H, which is written in this form. So, delta G is the Gibbs free energy which is written again in this form, and when T is greater than or equal to 1939, you can see that delta H enthalpy and Gibbs free energy return. The negative value of delta G, Gibbs free energy, in this equation implies a higher chance of TiC formation. In the solidification phase of 316 SSTiC composite, TiC is synthesized in situ from Ti and graphite. Ti reacts with the other material at high temperatures to generate in situ strengthening elements. So, Ti6 they do a in situ. In situ means during the reaction it forms. The formation mechanism of this in situ Ti6 composite is schematically shown below. So, you have a Gaussian distribution of laser beam hitting at a surface. So, this is the feedstock powder, wherein which you have, these are all 316 matrix, which is basically iron, and then you have Ti particle which is mixed, and you have graphite which is added. So, now you see there all the T316 matrix, Ti particles, C particles, they in turn react very fastly to form Ti6, and this Ti6 will be a particulate reinforcement in the matrix 316. So, when you look at this exothermic reaction which happens here, when the laser hits, it has a peak power coming here. So, here the laser hits, then Ti and C reacts to form TiC, and this TiC is getting dispersed in the Fe matrix. So, you can see molten, these are all molten 316L, which is basically iron, stainless steel which is iron. Okay. So, here what will happen is you can see molten Ti are here, and you also have carbon. So, now this gets transformed with the formation of TiC phases. So, these are all TiC precipitation which is there in 316L matrix. So, now this gets further refined, a TiC sized and ring like microstructure. You will see here 316L matrix and TiC phase which are getting formed. These are all TiC phase. So, now you can visualize how easily all these things happen by exposing it to a laser and trying to have it in one layer. So, initially it is 316L SS plus Ti plus C, giving you 316L, which is the matrix SS plus TiC. So, you can see exothermic reaction happening, then you will see a formation of TiC which happens, which are precipitated along the grain boundary, and then you will try to see refinement of TiC sized and ring like microstructure. You see all these things which are there. So, now it is very clear how do we form this composite. In powder metallurgy route, many a times what people do is they try to have 316 SS plus TiC direct they take. So, it can be like this or it can be like this. Here we can use selective laser sintering process or selective laser melting. So, you see that grain refinement has happening. Refined TiC size and ring like microstructure gives you a performance such that they can have very high properties whatever you want. The TiC reinforcement are found at grain boundaries, refining along precipitate, right. Ti6 reinforcement are found at the grain boundaries and inside the columnar dendrites in laser based additive manufacturing. So, columnar dendrites, these are dendritic structures which are formed, these are dendritic structures, these dendritic structures grow and in between maybe TiC will be formed. Higher solidification rates segregate TiC elements, causing this. Strong chaotic fluxes in liquid melt intensify heavy particles in the surrounding turbulence. Chemical inhomogeneity can affect the concentration contour and structural supercooling can affect the solidification approach and volume of TiC precipitate. The chemical inhomogeneity can affect the concentration, contour and structural supercooling. What is supercooling? We saw supercooling in solidification. Can affect the solidification approach and volume of TIC precipitate. So, the volume of TIC forming also can be played very nicely by choosing the parameters. So, the chemical inhomogeneity can affect the concentration contour. Small contact time and fast heat transfer can reduce TIC precipitation. When the laser is moving very fast and if the laser is taking to a very high temperature, then what will happen is you will have reduced TIC precipitation formation. Multiple laser scans over previously melted layer can increase TIC volume due to accumulated heat. So, you play with the heat parameters which comes into the process and you try to see how is TIC getting formed, how is TIC quantum could be changed easily. So, what does it mean? This tries to give me selectively reinforcement composite. So, what does it mean is I can selectively tune to increase in one zone. For example, if you have a zone of a composite like this zone you can have TIC rich, this zone you can try to have TIC lean, okay, and in between you can have a moderate region. So, now you are able to play with this property since it is additive manufacturing used here. The 316 TiB2, I am now changing TIC with TiB2, titanium boride. So, that was titanium carbide. So, titanium boride composite reinforcing components form a ring like structure. Generally, we try to use laser powder bed fusion method which faster cooling affects the composite. Due to grain advance time, higher cooling rate which goes up to 106 Kelvin per second limits TiB2 grain growth. This makes finer TiB2 particle. If you want to make finer TiB2 particle, this is one of the easiest and the fastest way of making it. Today, there is lot of research going in the area of additive manufacturing and metal matrix composite. The laser additive manufacture process temperature gradient causes a melt surface tension gradient. This gradient adds Marangoni convection to move TiB2 particles by limiting accumulation and regulating distribution across the cementide matrix. So, what is the other thing you have to do? See, first is TiB2, next is TiB2 dispersion. This dispersion should be done in a passive manner. That means to say, so the process itself tries to bring in that dispersion. So, that is what we are doing. How will the process itself? Because of the Marangoni convection effect. This gradient, what is the gradient? The temperature gradient. The temperature gradient adds to Marangoni convection to move the TiB2 particles by limiting accumulation and regulating distribution across the cementide matrix. 316 melts entirely, but TiB2 does not. This melts, this does not. So, Marangoni forces move the TiB2 elements. So, it pushes it when the liquid, it assumes that there is a river which is flowing and a boat which is there. So, the river when it's moved, the boat which is there, that also moves. So, that is what is Marangoni forces TiB2 elements. Matrix melting repels TiB2 particles, repulsive force and Marangoni convection generate a TiB2 ring like structure. The same TiC ring like, we also have TiB2 ring like structure. Same thing. So, now let us see the third variant of additive manufactured ferrous matrix composite H13 TiB2. So, H13 is exhaustively used for heavy industries application. So, here laser additive manufacturing in tool production allows for the digital production of intricately formed parts. AM reduces the cost of tools shortens the production time and reduces the personnel through robotics. Laser processed H13 TiB2 has Fe and TiB2 phase, but no austenitic phase. These structure may affect laser melting Gaussian heat distribution. Faster heating and solidifying cycle stimulate fine equiaxed grains with uniform TiB2 reinforcement along H13 grain boundary. During laser melting, when a full liquid forms, the dissolution mechanism generates strengthening phase by heterogeneous TiB2 nucleation and grain growth. It's all very nicely written. Dissolution mechanism generate strengthening. So, dissolution is what? You try to diffuse material into the matrix. So, this will try to strengthen phase by heterogeneous TiB2. So, you also have H13 TiC, almost the same thing. The laser faster heating and cooling cycle helps TiC structures happen by shortening the amount of time TiC grains need to grow. So, TiC grains need to go. So, we saw the TiC grain growth in this graph. Refinement of TiC cycle size and ring like microstructure, we saw almost the same thing is also common here. So, the laser faster heating and cooling cycle helps TiC structures happen by shortening the amount of time TiC grains need to grow. When the temperature goes up, the Marangoni flow gets stronger. When the Marangoni gets stronger, what happens? It tries to have lot of vortex. So, it tries to have more turbulent action, and capillary force pulls the liquid along. Movement can happen, Marangoni flow. The capillary force pushes the liquid alone. So, now there has to be both, and these two will try to disperse TiC, give you well dispersed H13 metal matrix composite. So, the shear and rotational forces, the rotation is through Marangoni, capillary is here. So, the shear and rotational force that form around the TiC particles could be a driving force for the particles to spread out evenly, which stops them from sticking together. So, there will be a shearing and a rotational force that forms around the TiC. So, TiC particle is here, this is TiC, and then there will be a shear and a driving rotational force, could be a driving force, TiC particles could be a driving force for the particles to spread out evenly, which stops them from sticking together. So, this motion of Marangoni force and capillary action tries to disperse TiC particles nicely in H13 matrix. I said passive dispersion is the best way. If you can disperse these reinforcing particles without applying a stirring action, then they easily disperse. If you do a stirring action, the mechanical force many a times does not give uniform dispersion. So, here this shear rotation force gives you that. Also, when the volumetric energy density is lower, the torque is less, which makes particles stick together more. So, we try to beat a trade off and try to disperse the TiC particles in H13 matrix. The last one in the ferrous is going to be with respect to tungsten carbide. Tungsten carbide are heavy and they are used for wear resistance property and hardness enhancing property. So, additive manufacturing ceramic arenas are interested in metal matrix composites strengthened with ceramic particles. Ceramic reinforcement ferrous composite perform much better. Tungsten carbide are high melting temperature and excellent wettability with many ferrous alloys. Why are we talking about it? Whenever you have an application, for example, you have a iron cable, through this iron cable there is current which is moving. So, now when we try to add these reinforcing agents, it can be carbon, graphite, graphene and other things. if you try to add them along with this tungsten carbide, it will try to avoid sagging. So, moment sagging is reduced. So, then what happens? The number of posts which are used for reinforcements can be reduced. Okay. So, here what happens? They always look for high melting temperature such that the deflection cannot happen so easily. High melting temperature and excellent wettability with many ferrous alloys are done by using this tungsten carbide. Tungsten carbide can maintain 1400 degrees Celsius room temperature hardness. Look at the amount of temperature rise it can give and maintain the hardness. Choosing the right reinforcing materials and matrix is the key boosting wear resistance, and therefore the interface is important. Iron based alloys are reinforced with ceramic component to improve their wear properties. So, this is the tungsten carbide particle. This is the dendritic growth which happens. This is an interface which we already discussed, and this is the eutectic phase of iron which is there. This is a microstructure which shows the morphology of matrix and matrix, interface and tungsten carbide reinforcement. The iron tungsten carbide composite dissolved tungsten carbide reinforcing component releases tungsten and carbon in the liquid metal. Tungsten and carbon atoms react with alloys to generate carbides near the grain boundary. The gradient interface MC3, M is tungsten, F is M can be tungsten, M can be iron, M can be chromium, N can be nickel, develops between tungsten carbide reinforcing element and the matrix during the laser additive manufacturing. It gives you a new, completely new compound, new intermetallics. All these things are formed in this additive manufactured route. Gradient interface may strengthen tungsten carbide and ferromatic and Fe matrix bond. Size and shape of the interface gradient fluctuates with laser power, intensity and spot size. So, this is very interesting phenomena, and here you can see it tries to form gradient interface. Iron tungsten carbide composite performance involves densification, gradient interface, microstructural morphology and hardness development. All these things are possible by using this Fe tungsten carbide: densification, gradient interface, microstructural morphology and hardness development. First, when densification is low at high scanning speeds, the material can be lost from the matrix due to pores. When you try to do with low scan speed, might result in increasing densification, which improves wear resistance. Second, the in situ reaction in gradient interface improves wear. The weak interfacial connection between the reinforcing component and the matrix is caused by composite wear. So, there is first and second. So, we have to go through it nicely to get to the output. The interfacial layers without porous and fissures ensures composite bonding. Thicker interface layer provide stronger bonding, making it difficult to wear away tungsten carbide components during the application, improving wear resistance property. The higher composite hardness can hinder adhesive process like scuffing and removing material, reducing wear rate and improving wear property. So, these are something which is important, like higher composite hardness can hinder the adhesive processes. We can also have vanadium carbide. Through laser powder bed fusion, vanadium carbide reinforcement ferrous matrix composite is also thought of. In this process, the laser energy and the pressure per flow in the laser stimulated liquid metal pool disintegrate micron size vanadium carbide through a melting solidifying mechanism. The laser light quickly heats the 316L vanadium carbide mixture, forming a molten region entirely dissolved vanadium carbide and 316L liquid. The vanadium carbide can quickly dissolve and release vanadium and carbon due to tiny particle size, high surface tension and laser heat. The tiny pressure of on ultrafine VC in the liquid melt pool accelerates the rapid melting process. It is very nicely process happens. So, how is V3 or V8C7 can quickly dissolve and release V and C separately. Ferrous vanadium carbide composite. The schematic diagram shows the formation of mechanism of ferrous matrix composite strengthening with VC in laser powder bed fusion method. So, you have part. So, in this you see there the scanning is moving from this place to this place. So, these are all fresh powder where still the laser has not come in contact. If you look at this very nicely, it is 316L powder with loose and bonded V8C7 particles of 316L surface layer. So, this when it is initially like this, you will have when the laser hits, you will have melted 316L alloy, then you will have atomic V and of decomposed V8C7, and you will have atomic C which is decomposed again from V8C7. So, here by laser these are getting split. Now, this nucleation of VCX happens. These are nucleation which happens. So, this gets diffused and other things. So, now from here you can see here it tries to nucleate of iron or chromium or molybdenum nickel carbide phase. The growth of VCX phase, you will have a solute and then you will have a solute atom of V. From here what happened, the nucleation grows and you have a nucleation and growth of austenitic grain. So, the cycle goes very interestingly like this. So, whatever V8C was there, it splits, then the splitting happens. Now, this splitting happens, you will have C separately, V separately. This V wherever it is there, the C tries to diffuse inside and forms a VCX. Now, this VCX then what happens, it tries to form a nucleation in the matrix. So, you will try to have nucleate Fe chromium molybdenum nickel phase with the growth, and then parallelly what happens, this VC which is there which tries to grow. So, then this will be the final nucleation and growth of the austenitic phase. After the laser source leaves the melt, it solidifies quickly. During fast solidification, VC and VCX develop through heterogeneous nucleation and grain expansion of VC nuclei. The matured VCX strengthening component will be disseminated at grain boundaries and in austenitic grains due to nucleation and progression. So, this is very important. The matured VCX strengthening component will be disseminated at grain boundaries and in austenitic grain due to nucleation and progression. When VCX phase becomes bulky, grain expansion pushes them towards grain boundaries. The VCX phase are retained within a austenitic grain. As laser AM have a quick solidification process, few V and C gets diffused into austenitic solution, solid solution. So, in iron it was, we saw very interestingly iron with TiB2, TiC, tungsten carbide and vanadium carbide. These are the four prominently used metal matrix composites made from additive manufacturing. Here now we were only focusing towards the grain boundary, grain refinement, Marangoni convection, flowing, dispersion and other things. We never discussed about process parameters, right? And now comes the shape factor, size factor of the additive manufactured part. All these things makes it really a complex phenomena for making metal matrix composite through additive manufacturing, but it is a growing area. In days to come, this area is going to pick up lot of momentum. Now, let us move to titanium and titanium carbide reinforced composite. The laser based additive manufacturing of TiC composite, different amount of Ti and TiC powders are mixed and milled with the ball mill to get a better density. Now, you see Ti and TiC are taken separately and they are ball milled. The TiC elements are made by laser AM through dissolution of or precipitation mechanism such as heterogeneous nucleation of TiC and the growth of grain. The X into construction of Ti, TiC, in situ is during the process, X situ is outside the process of Ti and Ti6, and the dispersion of TiC reinforced depend on the processing condition such as functionally energy density. At higher energy densities, the TiC reinforcing element spreads out in the form of a network array with the dendritic shapes. At lower energy densities, the TiC gets smaller and spreads out more evenly. At a lower energy densities, TiCs gets smaller and spreads more evenly. The lower energy density can also change the shape of the TiC from rough dendritic to a whisker like to lamellar it can do. So, rough dendrite. So, now what is happening is the energy levels whatever is there during the process can also change the shape of TiC formation. Higher scanning speeds causes faster cooling rates, which means that there isn't enough time for TiC to grow in the composite. This leads to change in improvement in the microstructure. So, lower energy densities, so TiC gets smaller. When you have higher speed rates, you can see that TiCs are formed, which means that isn't enough time for TiC to grow in the composite. So, that also tries to change the property behavior. When we talk about Ti, TiB composite, so TiB2 or TiB, people say, even though a lot of different particles can be used to reinforce TiC, titanium matrix composite, ceramic particles like TiB and TiC have gotten a lot of attention because they have good chemical stability. Like we see, it tries to decompose. Tungsten carbide, it also tries to decompose there. This makes it easier for the matrix and the particles to stick together and make the interface more complete. TiB is a steady element even with a very small solubility of boron in titanium, which is far low compared to that of carbon and nitrogen boron. Also, the thermal expansion coefficient of Ti and TiB are quite similar, which makes it less likely that a additive manufactured composite parts will have residual stresses. In contrast to the other elements like TiC, TiN, TiB2, TiB can also play a role in increasing the strength and elasticity of the composite. So, the solidification phase of TiB composite, you can see here TiB2 is formed and this is what is Ti. Okay. So, here if we see semi-reactive TiB2, so this forms in situ formation of TiW is there, and here you see these are all unreacted TiB2s. The schematic representation for the formation of TiB phase from the in situ reaction within Ti and TiB2 particles is shown here. A powder mixture with good dispersion of TiB2 surrounded by bigger Ti powder prior to sintering is like this. Then during in situ reaction develops needle like TiB, semi-reacted TiB2 and unreacted TiB2 are formed. So, the solidification phase of TiB, Ti in TiB is seen. Before sintering, the powder mixture shows that the TiB2 particles are well dispersed with the larger Ti powder. TiB2 is dispersed properly. With the in situ reaction makes TiB as well as TiB2 that are partially reacted and TiB2 that are not yet reacted. Ti, TiB2 powders are used to make in situ TiB composite, and the process parameters are optimized to make this happen. TiB2 has the highest melting point than Cp, closely packed titanium. So, it needs a higher energy density to melt. When Ti and TiB2 composites are made, they have two phases, Ti and TiB2. The in situ reaction occurs between TiB2 and Ti through the diffusional removal of boron from TiB2 or by melting or successive solidification of TiB. So, Ti plus TiB2 forms 2Bi. So, the formation mechanism of a three-dimensional quasi-continuous network of TiB is discussed here. The step 1 is laser power on the substance, on the substrate material will create the melt pool, which will capture powder delivered through a powder stream. Because of the higher input energy, Ti will react with B to form TiB. The recently developed TiB together with the other deliverable powder will be melt into liquefied material. This will be step 1. The step 2 will be when the input energy is moved to the next location, the liquid melt starts to solidify. Initially, TiB nucleates and progress as long whiskers offering heterogeneous nucleation position for liquid Ti. Afterwards, Ti melt will nucleate heterogeneously at walls of TiB whisker and homogeneously from liquid to develop beta Ti. So, this step sequence is very clearly written. Initially, TiB nucleates and progress into whisker. It forms a small lengthy whisker. So, that means to say diameter is very small, length is very high, offering heterogeneous nucleation position for liquid Ti. Afterwards, Ti melt with nucleated heterogeneously at walls of TiB whisker and homogeneously from liquid to develop beta Ti. As a result, beta Ti nuclei grow, pushes TiB into the liquid, which will not be submerged by beta Ti nuclei due to the poor solubility of TiB in beta Ti. So, we are just saying how is this beta Ti coming and how is it getting formed in nucleation, so that these composites can be formed. Step 3 will be TiB whisker accumulates at Ti rich grain boundaries, develop QCN like structures. Meanwhile, beta Ti gets converted into alpha Ti. The formation mechanism of three-dimensional quasi-continuous network TiB2. I am trying to deal this in detail because the schematic diagram whatever we have presenting here will try to explain. Almost in the similar fashion you will have for ferrous also. The SS316L also you will have a similar mechanism which is going on. So, you have to go back to the phase diagram and then do it. So, here if you see Ti particles along with B are the B is located around it. It is a schematic diagram. So, they are located around it. So, now what we do is we keep it as a workpiece. Now, we try to expose it to laser beam. In laser beam there are two things, fast, slow scan, and then you have another two more which is nothing but high power and low. So, these two, this is for power, this is for speed. Okay. So, with this what will happen, you will try to melt the material. So, a pool is getting formed. So, when the pool is formed, you see first in this laser radiation you see completely it is molten. Now, in the second stage what happens is you have two things, one is called as homogeneous nucleation, the other one is called as heterogeneous nucleation. In under homogeneous nucleation what you can see is you can see there these particles are there and then these particles are beta Ti. These are beta Ti nuclei. So, it is there and then you have a whisker like structure. When you try to see the heterogeneous nucleation, you see that the spots of beta Ti are there and then you also have some amount of small reinforcements which are getting formed. When it goes to this phase is called as a solidification phase and undercooling also happens here. Now, from the solidification phase it will try to move towards the last phase of DQCN formation, which is nothing but dimensional quasi continuous network formation. You can see here this is the grain boundary, you have Ti grains and then TiB sitting along the grain boundary. So, this is how you try to get this TiB getting formed. So, you can also try to do with hydroxyapatite, which is very common nowadays used for biomedical applications. So, titanium mixed with hydroxyapatite composites for making bioimplants. Here the bioimplant has to have cell adhesion plus it has to have strength plus it has to have toughness. So, they try to mix all these things. Even though Ti alloys have good properties for biomedical use, bioactive ceramic reinforcement like hydroxyapatite could make the osseointegration even better. HA, hydroxyapatite, is a calcium phosphate compound that has the same chemical makeup and shape as bone tissue. So, we are trying to mix these two. Nano hydroxyapatite, which is N, has gotten a lot of attention as the biomaterial for use in prosthetic because it is similar to human bone tissue in size, shape and chemical makeup. So, if you see here the solidification phase of titanium with hydroxyapatite composite, the reaction takes place through the laser powder bed fusion method is calcium phosphate which reacts with gas which forms Ti and H2O, TiO2 and 2H. The same thing when it is mixed with TiO2, this is the chemical reaction, it releases hydrogen, it forms calcium CaTiO3 and then half O2. Then this calcium phosphate plus half oxygen plus 3 Ti leads to the formation of calcium CaTiO3 plus 2 phosphorus. 5 Ti plus 3 P forms Ti5P3. So, this is a very interesting phase. The laser powder bed fusion phase generation method for Ti nano hydroxyapatite is as follows. Calcium phosphate component reacts with the phase to create Ti5P3, then Ca3P4 twice CaTiO3 and Tix, which is we have said 2 TiXO during hydroxyapatite breaking. The Ti5P3 and calcium PO4 twice remains dispersed throughout the matrix. So, CaPO3 remains after CaTiO3 is synthesized. The low oxygen absorption during the production causes TiXO phase, not TiO2. The hydroxyapatite oxygen diffused into Ti matrix and creates titanium oxide. The faster laser powder bed fusion solidification causes saturation forming TiXO along lathe shape grains and CP structures, closed pack structures. Ti nano hydroxyapatite in Ti matrix forms tiny acicular shaped grains. So, this is what it is. Solidification phase of Ti hydroxyapatite component, grain refinement. There are two stages. One is generation of dendritic crystal, the another one is connection of dendritic crystal. So, you have long lath shaped grains, these are long lath shaped grains, and then this on heating will try to with 2% of hydroxyapatite will try to form short acicular shaped grains. So, you see here these are all acicular shaped grains, and then this on further mixing with hydroxyapatite to 5%, it forms quasi continuous circle shaped grains. So, with 0% only Ti or Ti plus 2% Ha and with 5% Ha, you form generation of dendritic crystals, and then here you will try to have connection of dendritic crystals. The solidification phase of Ti hydroxyapatite composite is how the microstructure changes when hydroxyapatite is used has to be with how fast the melting pool moves and how different nuclei forms. So, all these things are very important to make a very good titanium rich or titanium reinforced with hydroxyapatite. The lower amount of hydroxyapatite can shorten the spherical grain without making them too dense, while a higher amount of hydroxyapatite slow down the growth of crystal and let almost continuous spherical grain form. With the addition of hydroxyapatite, the microstructure of composite made with LPBF gets better and better over time. In short, the grain's shape is changed in a unique way as follows: long grains shaped like a short grains with a round shape, quasi continuous circle shape. This is very important, you should know. The unique way as follows: long grain shaped like lath, short grains with a round shape, quasi continuous circle shaped grains. Today we also make TiB2 metallic glass composite. So, metallic glass means they show properties of metal as well as glass. So, they undergo this glass transition temperature behavior is also undergone here. The use of zirconium based metallic glass Mg reinforcement can open up a new way to change the microstructure of titanium metal matrix composite by stabilizing the face and reinforcing both the face. This can make titanium metal matrix composite part stronger and more flexible. The Ti6Al4V liquid melt usually solidifies in a planned way because the temperature difference between the liquidus point and the solidus points is very small. On the other hand, adding Mg metallic glass to Ti6Al4V alloy may disrupt the equilibrium process, causing the solidification form a change from planar to dendritic structure. This type of conversion takes place when the liquid phase obtain a thermal gradient below the critical value near the solidification front. This is very important, takes place when the liquid phase obtains a thermal gradient. Liquid phase obtains a thermal gradient below a critical value. So, the critical thermal gradient delta T by delta X is given by C naught 1 minus K delta TL liquidus line divided by DL the R K times delta C. C naught is the solute concentration, DL is the solute diffusion coefficient, R is the solidification rate and K is the solute participation coefficient associated with the coefficient solidification limit among the liquidus and solidus line. Because of the different densities of Ti6Al4V and Mg metal, a gravity force will act on Mg melt to settle down the melt. The dynamic viscosity nu for the liquid is given by this, which we talk about kg per meter second. Theoretically, owing to the higher density and viscosity, the Mg melt leans to separate from the Ti6Al4V melt. In addition, the beta phase becomes stable by copper and nickel and then passes through a solidification having a higher melting temperature. The dendritic formation, these are the elements which play a very important role to do the supercooling of melt and which enriches melt pool with Mg. Addition of faster cooling process restricts the growth of amorphous phase Mg, and however Mg nano band can pass a partial crystallization during continual heating of layer by layer deposition. Thereby a hard soft nanostructure melt composite can be formed by using AM structure. This is what is the mixture of boron carbide with Ti6Al4V. So, you have a melt pool, you have a alpha phase which is there, and you see these are beta phase and these are all Mg nano bands which are formed in the reinforcement, and this copper, these are also copper zirconia are also formed as nanocrystals during the process. So, TMC manufactured from the mixture of Ti6-4LV plus B4C powder with different volume content of B4C follow the in situ chemical reaction of this. So, this is for B4C pre-alloyed composite, you can see TiB and alpha beta Ti matrix. So, the Ti4b affects solidification in several ways. Beta Ti can form as the first solid phase during solidification based on Ti phase diagram. The boron rejects the liquid with alpha beta. So, it is not necessary everything will be accepted, it also can reject, causing micro segregation of B near grain boundaries and eutectoidic solidification. Fine Ti whisker stops grain expansion, and alpha Ti grain variation may cause boron macro segregation during solidification. So, the boron segregation near the melt pool creates a partial remelt region in the subsequent layer, improving the grain structure. TiB whisker affects the Ti6Al4V plus B4C. The carbon in the beta Ti solution contributes to hardening, and TiB network like structure around beta Ti grain increases composite rigidity. Now, let us look at assignments. There are 2 assignments which I will give. So, you try to see TiB2 reinforced composite, TiB2 reinforced composite application. Where do they use this metal matrix composite? Next one is when we talk about TiHCA hydroxyapatite, what all implants are being attempted today as MMC through AM process. Okay, these two will give you an insight of the process or insight about the formation of the microstructure and other things. Thank you very much.